Our next presenter is Caleb Jew from Georgia Tech. His field is operations research, and his advisor is George Land. He did 2 practicums, the first at National Renewable Energy Laboratory, and most recently at Lawrence Berkeley National Lab. Please welcome Caleb.
So, hi everyone. Today we're going to be talking about reinforcement learning, which I've been working on for the past few years. If you're familiar with it, you may have heard about it from like an AI context where it's being used to beat the best players in Go, or even recently being used to train some of the state-of-the-art large language models. I'm gonna motivate it a little bit differently and tell you about some of its applications in computational science. So here are some applications that I've looked at or worked on. So one is in chemical engineering application called waste biorefining processes, where you try to tune some knobs to control the flow rates to get energy that's good. One application I'm really interested in, which is really catalyzed by the CSGF's practicum, POS, and also just the flexibility work with other faculty, is this power of battery energy storage systems. What you see here is actually a picture I took during my practicum of some solar panels at NREL outside the parking lot. And let's imagine you connect it with a battery. You could imagine where this is a problem where you want to find the best way to operate your batteries so that you maybe maximize your profit. So maybe during times when the electricity is very expensive, you decide like, let's just charge right now with the solar panels, but then later on you predict that around 5 p.m. the price will be quite expensive, and then you'll sell electricity back to the grid. And what's common along all these applications is you need to make decisions, but you need to make multiple decisions over multiple periods of time frames, and you need to do this in an environment that's highly complex, nonlinear, and you're also facing uncertainty. So this is quite a difficult challenge. So what I'm going to do in the first part of my talk is kind of introduce you to the problem mathematically, then I'll tell you about some fundamental gaps that we tried to address. So the mathematical framework we're going to be working with is called Markov decision processes, and I think this picture does a pretty good explanation of what's going on. We're really trying to model an interaction between an agent or decision maker and then an environment. So there's many applications where this arises, and the goal of the agent is to make action or decision every time frame. So you can see this action gets fed into the environment, then the environment receives it, and then it processes it into the next time step. So internally within the environment, you have some states, which is the configuration of the world, and you also have some rewards, which tells you how favorable your configuration currently is. Also, this environment changes dynamically over time. So you also have some dynamics denoted by calligraphic P, which kind of describes kind of the physics of the world, like how everything changes. And your goal as a decision maker is to kind of optimize your agent. You want to find the best set of decisions over a long time horizon. And we also include a discount factor to weigh future decisions, less importantly, in the present decisions. And so now I can briefly describe to you what reinforcement learning is. So I just described to you that mathematical decision-making framework, and all that reinforcement learning is a data-driven approach to solve such problems. So to put it more succinctly, and when you solve Markov decision processes, or MDPs, you typically know everything about your system, including how the world changes. On the other hand, in RL, you know everything but how the world changes or your dynamics. And so you have like an implicit representation through data, and this is where the data-driven approach comes from. So instead of knowing P, you only know some data that's drawn from some distribution that's kind of defined by your transition. And when you talk about data-driven processes, you also need to define how your data is generated. So 3 popular paradigms are going to be shown here. And to kind of give you some intuition, let's think about training a self-driving car, because recently in Atlanta, we started rolling out those Waymos. I thought it'd be kind of a fun example to go through. So let's say you have a lot of training data already, like you hired a startup and they have a large corpus of data. We call this the offline model because you have the data already before you do any training. On the other hand, there's some other examples called the online model where maybe not all your data is available. And so you kind of have to take the data on the fly or one by one. And so one possible approach for online is the online generative model. My younger brother loves playing racing games, so think about the online generative as like you're playing a racing game, and if you take the turn wrong or you crash, you can always rewind or change your course. So you have a lot of control over how your data is generated. A more realistic approach, but more difficult setting is this online trajectory model. think about this as you're an engineer at Waymo, and you decided, I want to drive my car on the streets of Atlanta, but you can't choose when to switch roads all of a sudden, or you can't reset. Like, you have to kind of follow the laws of physics, and you kind of have to make mistakes and kind of work through that. As you might imagine, this is a more difficult setting because you can't control your data. And also, because the data is kind of correlated across time, you have some additional errors. Okay, so this is the problem setup. Now, to formulate our RL problem, we can actually formulate it through optimization, where the goal is to find the best decision maker that kind of optimizes our objective function. And for us, our objective function is the so-called value function. We have a very complicated formula, but I like using words, so I may not tell you what each of these components corresponds to. So this objective function involves randomness, so we have some expectation. It involves decisions, which have costs every time period, so we have costs over multiple periods of time, as well as decisions we need to make over multiple time steps. And also we have this very complicated, nonlinear, possibly random environment. So our goal is to try to optimize this and get the best decision maker. But this is a very complicated function, so we need to kind of resort to approximation schemes to solve it. So a popular approach, which for those who may train neural networks may be familiar with, is gradient descent. And the intuition behind gradient descent is I have a very complicated function, but I can at least understand what it looks like in a small region. And within the small region, I'm going to kind of improve within the small region and just repeat that process over and over. We're going to take the same idea, propose this policy gradient method. So we're not the first ones to propose this, but this has been studied for a while and also used in practice. But the main gist of it is, as I said before, this is an iterative process where in every iteration T, you need to perform just 2 steps. Since it's a data-driven approach, we're going to first sample some data, call it DT, and then we're going to use that data to estimate the gradient of our objective function. Once we've done that, then we can move to the policy optimization step, where we use that gradient to form a local approximation of our objective function. We improve it within that local approximation, and then we just repeat, and we do this over and over. So this is the algorithm, and it looks very simple, but you're going to see that there are some fundamental gaps that really haven't been answered satisfactorily, in my opinion. So we're going to go on to the second part of my talk, which is telling you what are the gaps that we saw, and how do we resolve this using like mathematical techniques. So the most fundamental issue, in my opinion, is if you go back to the previous slide, I mentioned that this is a data-driven approach, so you need to estimate some data set DT. What I didn't tell you is how to get this data set DT, because one of the main issues in reinforcement learning is the exploration-exploitation trade-off, where you don't want to spend too much time gathering data, because this means you can't improve too many times. But then if you do not enough samples, then maybe you don't have a rich enough data set, and you have a poor estimate of your gradient. So this is a question of what's the right balance so that my data set is rich enough to get a good estimate of my gradient while not spending too much time on it. This issue is exacerbated by the fact that the data set quality is also kind of affected by the data correlation. This is also affected by some unknown parameters from your distribution, which you know nothing about. So we're really trying to kind of balance a hard problem while not knowing anything too much about our problem a priori. So this is kind of one of the fundamental issues of reinforcement learning that we don't think has been answered satisfactorily. And finally, another issue which I'll kind of brush upon at the end is, in addition to these challenges, when we try to scale these problems to high-dimensional problems, which might arise when dealing with PDEs or multi-agent settings, how do we ensure that these methods remain scalable and work in high-dimensional settings? And I'll show you some kind of early empirical ideas to answer these. So for our first set of results, these only concern the simpler setting where the number of states or actions is not too large. Think about this as your environment is not too complex. The reason we need this is so that some of our techniques kind of require a bit of a brute force approach, but they're still pretty efficient. So what we first uncovered is that there's this new implicit exploration phenomena. So previously, what many people assumed is that your data set automatically is rich, but I think this is an unreasonable assumption because this means that you make some assumption about your data set, which may not even hold in many real-world scenarios. So what we show instead is that if you show that there exists an optimal decision maker that's exploring, then we can guarantee that when you run that previous algorithm, every data set is rich enough for you when you run long enough. And it's actually, the duration you need to run is not too bad. So this means that without making additional assumptions, we can get the same type of convergence And we do so kind of for free just by making this existence assumption. One thing I hid under the rug, though, is that for this to work, you need to know how correlated your data is. So you need to know something about your data without knowing what your data is. It's kind of like a paradox here. So to kind of overcome this, our second set of results concerns a new class of certificates. You can really think about certificates as knowing something without knowing something. So we basically derived this for both policy evaluation, which is the grading estimation, as well as the optimization. And they kind of give you a taste of what this looks like. Let's say you're training your reinforcement learning algorithm. And let's say this top blue line over here, the dashed blue line is your current status. But you want to know, am I doing well or am I doing poorly? And what we showed is that we were able to construct a certificate that gives you an estimate of the optimal value without knowing the optimal policy. And our estimate is this other dashed blue line. You can see that it actually moves very close to it, so we have some form of confidence that we did well. We also compared this to some other kind of more heuristical certificates, and we found that ours gives you the tightest bound, while everyone else's is kind of far away from what the true value is. So this is very promising results, but as I said before, this is really for the setting where the number of states or actions is not too large. But in many real-world scenarios, you often have to face high-dimensional settings. So what happens if you need to deal with this inevitably? So the approaches we developed here are a little less theoretical, but more empirical, but we believe we have some initial steps towards getting some good results. So we proposed this adjustable exploration framework, and to kind of motivate it, let me tell you that when you're dealing with these high-dimensional settings, you usually are using some form of function approximation, such as neural networks. But if you ever played around neural networks, you know there are a lot of knobs to tune, such as your learning rate, what activation function you want to do, or how many layers you want to use. So this makes it more challenging to implement in practice. So our hypothesis is that if you introduce this additional technology, there are more knobs to tune, but we believe that there's only a few parameters that are important. We're going to leave that for the user to decide, and all the other parameters we're going to kind of use like traditional hyperparameter optimization. And these are typically, you can kind of do it in parallel, so these processes are typically embarrassingly parallel. So you might be asking, what are some of these parameters that influence the performance the most? What are the important ones? And one that we found is the type of exploration you use to solve your problem. So for solving this control problem called the inverted pendulum, we added some of our own additional noise to the policy. And we found that we added two types of noise, of mixed noise and Gaussian noise. And what we found is that if you use Gaussian noise, you get over 8-fold improvement over adding this mixed noise, which is kind of a hybrid of uniform and then Gaussian. So we found that the type of noise and the amount of noise highly impacts your performance. And we believe this is one of those parameters we want to leave for the user to tune, because they can decide like, okay, maybe I want to be more risk-taking it and do more exploration, while some others may want to be more risk-averse and then do less exploration. We also implemented this against some other control frameworks. And we found that for some settings, we're able to get the noise right. And then for our algorithm in the purple, we're able to get better performance than other methods. There's some other methods where the exploration is a little more intricate, so we can't get as quite of a good performance. Our purple line is kind of stuck kind of between in the middle. So this is something we're still actively working towards. Okay, so to kind of bring everything together, this talk is really kind of introducing what reinforcement learning is and tell you about the fundamental issues. And I think it really boils down to how do you do exploration. And we show that when your model is not too complicated, so you have not too many states or actions, we basically show you that your algorithm can automatically explore, and we give you some certificates to tell you when's a good time to stop exploring. On the other hand, for the more challenging setting where you have a large number of states or actions, we found that you typically need to do more heuristical approaches. We believe we have some initial steps to make this more friendly to implement, where we let the user decide what are the important parameters, and we use computation to solve the remaining parameters. So that's my talk. I just want to finish by acknowledging my advisor and the many collaborators I had from my university and my practicums at NREL and LBNL. It really kind of helped diversify my portfolio of research. I like to thank the Krell Institute for giving me lots of flexibility to pursue research that I normally wouldn't have, especially in the applications of power systems. I'd like to thank Krell staff, Lindsay, Lisa, Michelle, and Robin, and many others for making this a premier fellowship, in my opinion. And finally, all the CSGF fellows. I think one of the best perks of this fellowship is the people I meet. And so I can't fit everything on one slide, so I'm just showing the first time I ever met the fellows, which was in SC 2021, where there's an Alfredo pasta, and then people kind of scattered throughout the table. So thank you.